calculation. So you have a current source here. Just for this single device, this frustrated me for many years. I mean, the teacher in the college just didn't tell you what I told you guys. They just have a current source in the circuit and ask us to do calculations. And never say just, a lot of times people need to, you have to emphasize it, saying, for example, it's going to force the current in that channel to be 10 microamps, right? If you don't say that, a lot of times they are thinking about, I'm going to calculate the voltage here, I'm going to, calculate the voltage drop across the current source. You just don't have to. It's just tell you that the current is going to flow in here by 10 microamps. It's just some model only exists in the textbook. It's okay. It's just for calculation to practice.
So it's not splitting current.
No. Current is a dielectric material. It's a DC current. Did I tell you this has a frequency over there?
No.
Nothing. It's a DC current. It's blocked. It's just flowing in here. Gotcha. It's going to force a 10 microamp current in the channel of the MOSFET. And remember the square law equation? Here's IDS, right? Drain, source, and IDS equals KPN, which is given, width over length, and VGS minus VTHN square. So there are only two. So here's a variable, here's the result, right? If you know VGS, you know IDS. Why? Because this is an equation for the NMOS is being operated in where? In the saturation region. Okay, it's in the saturation region. And why do we know that this is being operated in the saturation region, but not trial or cutoff? How could you tell that? Remember, where's the saturation region and what's required? What's the x-axis for this IV curve? What is x here?
Yeah.
Threshold voltage. This is VDS. And this point is called what? What's the name of this point? VDS set. And this equals VGS minus VTHN, or VTH for the NMOS, right? Okay. And here is the saturation region. In order to operate NMOS in the saturation region, you need to have a VDS larger than what? Right? Just look at this curve. VDS needs to be larger than that in order to get into the saturation region, right? So for this circuit, I short G to D, right? So what is VGS? Well, what is VDS right now? VDS equals what? Right? It's the same node. VDS and VGS, same thing. What is this? Right? So this is always larger than that. How much larger? VTHN, right? 0.8. So this is always larger than that. So which means if you have a connection, if you short gate to the drain, it should be operated. Yeah, it should be in the saturation region. Yes. As long as you don't have a huge resistor on the top. If you have like 1 mega ohm or something, it will force this one into the trial region because this one just drops so much voltage across it, so it won't have a large enough voltage to turn it on. As long as you have a reasonable size for the resistor, it should be operated in the saturation region for the transistor. So that's why when we have this connection here and we force a current. So one quick question: if I force a 10 microamp current in here, if I don't make this connection, do I know which region this is being operated in? You actually couldn't tell. But 10 microamp is not, it's quite a few amount of current. So whenever it's not in here, it's in here, it's usually just maybe picoamps or something. And in the trial region, it can be in the microamp range. So actually you couldn't tell. If this is in trial, which is trial region or linear region. Yeah, trial region. I forgot. I forgot actually.
And VTHN is the threshold voltage for the endpoints.
Yeah.
Let's just use linear. I think this is the name we use in the textbook. And here's the saturation region, here's the linear region. And you couldn't tell because just know the current. You don't know what's the VGS and VDS here, you couldn't tell. So VGS must be VDS must be larger than VDS set in order to operate this in the saturation region. If you do the connection, connect the G to D, it's going to satisfy this condition here. So that's why it's in the saturation region. That's why you can use this equation here. So you don't want to directly just put it on your homework. Directly use it without saying this is in the saturation region, since you couldn't know. You don't know that, right? You have to say this is shorter to here, so it is being operated in the saturation region. So I can use this spiral equation to calculate what? No, IDS is given. That's in the model file. VGS. Is that interesting? You'll learn a lot in the future if you stay in this field. So this is IDS is the most important parameter in all these MOSFET calculations. It's called bias. Where you bias this transistor or op-amp. Okay, if you bias this transistor using 10 microamp IDS, you are having a specific VGS, which means you turn on the valve of the faucet to a certain level, which is called a bias. You bias it to a certain level or lift it to a certain level to operate that transistor. It has all different, you can consider that the NMOS transistor, even though it's the same transistor, but it has different operation modes, right? You turn it on with one VGS, it's being turned on one specific mode. It has all the corresponding parameters, for example, the AC gains and bandwidth, things like that. We're not calculating that in the digital class. But just let you know, the IDS, VGS are the most important parameter. Two parameters in MOSFET calculation. But if you know IDS, you got VGS. You know VGS, you got IDS. Because of square law equation.
Those are the only two unknowns.
Yeah, for large process. This is the 1 micron technology.
What's KP again?
KP?
Yeah, KP.
Yeah, KP is 120. It's given. It's given. Yeah, it has cogs and togs.
That's the P, the holes for the N type.
Hole concentration.
Yeah.
And mobility, and all those kind of things. I forgot the equation to calculate KPN, but it's given for the 1 micron process in the model file. It has the capacitance of the oxide layer, the thickness of the oxide layer, and the mobility of the electrons. I think it's probably mu cox, right? Like that, something like that. Mobility times cox. I don't want to give you the wrong answer, but it's.
I was thinking candles.
I saw something about that.
Yeah, I'll look into that and burn it over here next time on Friday.
So this equation also works for
P-type.
PMOS,
Yeah,
right?
PMOS is just to change this to VSG and change this one to VTHP. That's it. And here's KPP. So for KPP, I think KPP is 40 microamp over square voltage, but KPN is 120. So here's a very quick question here. Why KPP is smaller than KPN? Why is that? So I just told you the mobility is a multiplication of the mobility and the oxide layer capacitance or something, right?
The mobility of holes is smaller.
Yes. Yeah. So they move slower. Mm-hmm.
We're confident with the basic physics.
So in your homework, you want to use 40 microamp
Yeah.
per voltage square for PMOS and 120 for the NMOS. And you probably will see that the threshold voltage in the model file for the PMOS is minus, I think it's minus 0.9. Since we are using VSG, so we just ignore it. So VTHP is going to be positive 0.9 for the calculation here, which makes things a lot easier. Because directly use VSG minus 0.9, and here's VGS minus 0.8. Okay. This is asking you guys to calculate for VGS. And you don't want to directly, you don't always use this equation if it's just calculating VGS, not IDS. This is for calculating the IDS, right? But you have to transform it. It's the same, still the same equation, but transform it to like VGS equals something. I mean, it's very easy to do that. So VGS equals, remember we named these three parameters as beta n, right? Just combine them together and rename it. So this becomes what? 2 IDS, right, over beta n plus VTHN. Right? Look at it. Move 2 to here, 2 IDS, and divided by beta n, and equals this square, right? So that's why you get a square root of it, which equals VGS minus VTHN, and then plus VTHN equals VGS. So for this problem, you just directly plug in your IDS into here, and beta n is given, as is given, to calculate for VGS and verify using LD-SPICE. Very simple. Any question on this? Have you suffered? Why do we put PMOS on the top and NMOS at the bottom? You did a lab yesterday. Yeah, but why we have to use, it's called complementary. It's called complementary MOS, right? Yeah. So PMOS is good at passing You just turn it on, like PMOS and NMOS are just transistors. You turn it on, it passes the potential over to the other side, other terminal, right? So PMOS is good at passing VD, and NMOS is good at passing ground. Why? So now we're going to introduce pass gates. Pass gates. It's like this. Okay, you turn this on like a switch. You turn it on, it passes something here to here. So we're talking about the voltage potential, right? So now let's see if we use the NMOS to pass a zero, because I just told you NMOS is good at passing ground. And now let's see why it is pretty good at passing a ground. So for example, I have a ground here already. Okay, and since I want to pass it, do we want to give a gate a higher voltage or lower? 0, 1 in order to turn on the NMOS? 1, yeah. Okay, and initially here's a cap that stores a charge or something, and you have a switch here, right? You close the switch at some point to discharge it, discharge the cap to ground. Or you can consider that I'm trying to pass 0 to here, because originally it has a V potential being held by the cap at the very beginning. Right, turn on the switch, and because VGS is 1, right, so it's on. So this guy is on, and if you rotate it, I'm trying to pass 0 to here because I'm discharging this point. Make sense? Discharging this cap to that point. So my question is, are you able to, or I can say, so it's discharging that way, right? Discharge the cap in this way, or you can say it's passing 0 to the other way, right? To the top, to the cap. So the pass gate is passing. I turn it on, it passes 0 to here. Can I pass a 0 to here? Can I fully discharge it?
The capacitor?
Yes.
Yeah.
Why?
Passing 0 to it, aren't you?
Yeah, is the NMOS always on when during the discharging process? Is NMOS always on?
If the gate's on, yeah.
Yeah. Why is always on? So one logic 1 is 5 volts, for example, right? So I have a G here, I have an S here. It's symmetric structure. So I can define S here, doesn't matter. I just do it one way. It's going to be equivalent to the other way. So VGS, because this is a strong 0, I'm trying to pass a 0 to here is a strong 0. So VGS is always larger than VTH, right? It's always on. So it's going to discharge the cap until it reaches 0 volts. So the question is NMOS good at passing a 0? Yes, yes. Eventually it's going to be 2 zeros, right? Make sense?
Yep.
So what if I charge a cap? Just charge it up. I have an NMOS here. Here's a cap, initially nothing. And then here's a switch, for example, right? And here's a logic 1 here. It's a strong logic 1, like a VDD. Has infinite amount of charges in there. Okay. Before I do anything, there's no power. So the voltage here is 0, right? Initial voltage is 0. It's not holding, was not charged up, so it's 0 volts. And I turn it on here, turn it on. Logic 1, give a logic 1, and I close the switch. What's going to happen? It's going to charge up the cap, right? until when? So this is trying to tell you if this NMOS is good at passing a 1 to here. Eventually, can you get a 1 here or not?
No, because eventually the capacitor pushes back.
Why pushes back?
It's fully charged. Oh, wait, never mind. No, forget. I think the read.
So keep in mind, here's G, here's S, right? For example, this NMOS can pass the entire 1 to here. Okay, so it's fully charged to 1. What is VGS? What is VGS? And I'm asking a really simple question. I know you guys are tired.
What is it?
VGS, if this cap is fully charged by 1, yeah, what's going to happen? It's off. So could it reach 1 actually? Yeah, so it runs like that. So I close the switch, then the charges start dumping into the cap, right? Start building up charges. And whenever the voltage reaches some point, which makes VGS less than VTHN, it's going to shut it off. So it won't charge it anymore.
As the cap is charged, VGS goes down. Potential between
Because you need
okay.
you need a VGS larger than VTHN in order to turn it on, right? Keep it on. If you don't have a channel, if you don't even have a channel, you won't be able to charge this up because there's no connection. Mm-hmm. So what's the largest voltage can be reached at the cap? So for example, this is called VDD, okay? VDD. And for digital circuits, logic 1 is, what's the voltage for logic 1? VDD. And VDD start charging up the cap until some point, which the voltage is this, until it reaches this point. It won't reach VDD, it's going to reach VDD minus 0.8. Then what's going to happen is, because this is a source voltage, this is a VS, right? And your VG is VDD. So you want to get VGS, just use VG minus VS, which is VGS. This equals VTHN, which is the lowest voltage to turn it on. Let's do it again. So when VDD starts charging up the cap, could it charge it up to VDD? No. It's going to start rising, right? From 0. Rise, rise, rise. Here's VDD. It won't be able to reach VDD. It's going to reach somewhere below it. Yeah, what is that point? Why? Because this is VS. And VG is always on, so VG is always VDD, right? So VG minus VS is VGS. And this becomes, whenever VS reaches VDD minus VTHN, your VGS equals VTHN, which is the lowest voltage to turn it on. It's a threshold voltage.
So it won't ever turn itself off. It won't be able to.
It will be off eventually. And it's not going to charge it up anymore. It's going to turn it off, right? After it's getting super close to this point, it's almost off. Very few charges are still flowing into the cap, and gradually just nothing later on, whenever it's getting very close to this point, and no charges later. Okay. And then everything is shut off. So the cap's going to store that VDD minus VTHN voltage in there, so hold it in there. So my question is, if you're trying to use a NMOS to pass VDD, can you pass the entire VDD over to the other terminal? No. So how much voltage is being lost?
VDD minus VTH, that difference.
How much is being lost?
Yeah. Oh wait, that's just VTH?
Yeah. Cannot reach VDD, can only reach VDD minus VTHN. So the difference is VTHN.
Yeah.
That's something is being lost, right? You couldn't receive the entire VDD on the other terminal. It's going to be VTHN less. Make sense here?
Yeah.
Okay. What about PMOS? PMOS is good at doing what?
Passing VDD.
Yeah. Let's see. This guy is doing his job. GS, and we are trying to have a switch here and VDD here, right? Close the switch, start charging up the cap. Initially, the cap has 0 volts on it. Here's VSG. Now, close the switch, starts dumping charges to the cap. Until what? Until when?
Until VDD, but well, the passively though. So
Who can cheat here?
I don't want to cheat, I want to learn. I know it's good.
yeah, it's fine. It's like, I know it passes, but I don't know why it doesn't.
I didn't ask you why. I'm going to ask you why if the next question. I'm asking you, can this cap reach VDD?
Yes.
Yeah.
Good job. And then why? So stars. Hey, so if I turn on, I'm trying to turn on the PMOS, right? What's the voltage to be applied to the gate? No, you are looking at VSG, so you need a VSG, S2G, right?
Okay.
VSG must be larger than VTHP, which is 0.9 volts, in order to turn it on, right? So now you are looking at the potential drop from S2G. You need a 0 volts at the gate to turn it on, which is logic 0, which is just 0 volts, ground.
So I'm still like processing. You need a logic 1 to turn on the NMOS.
Yes.
Logic 0 to turn on P.
Yes.
To the gate.
Yes.
When you turn on the gate, it allows
Not turn on the gate. You have a
turn on the P.
turn on the. You are looking at VSG or VGS, the potential drop, not the absolute voltage at the gate. So if you have 5 volts at the gate for the NMOS, and you have 10 volts at the source, it's not going to turn it on. But for the PMOS here, you look at that, the condition here, you close the switch, this voltage becomes VDD, and this voltage is 0, so VSG is VDD. It's good, so turn it on. This is larger than VTHP, right?
Yeah.
Always look at the VGS or VSG, okay? And then this starts dumping charges to the cap. So the voltage at this plate starts rising, right? Until VDD. So what if I have a VDD here? When it starts charging this up and it reaches VDD, is there anything gonna shut off this transistor? It's not affecting anything. Whatever voltage here is fine. It's just SD. You're trying to say SD? Oh, GD? No. VSG, right? So VSG is always VDD minus 0, so it's always on. So this voltage is going to pass to the channel and reaches the cap, charge it up to VDD. Okay. So what about passing a 0? So this is good. PMOS is good at passing VDD. It's verified. And if I pass a 0 through PMOS, what's going to happen? Here's 0. Initially has a V here, right? And forgot for that again. So I close the switch. Here's a strong 0. I still want to turn it on, right? So I need to give a 0 volts to the gate. But initially, here stores VDD in here. Is this VDD infinite or it's finite amount of charges? Because it's in the cap. It's not a source, right? It's not a voltage source being plugged into the wall. It's a cap, and it's going to discharge through the channel because VDD minus 0 is VDD. So the VSG is larger than VTHP. So it's going to be on, right? At the very beginning, it's going to be on. Until when? It's going to stop discharging to 0.
So VDD runs out.
So,
Wait, oh,
so VDD is less than.
yeah.
So VSG must be larger than VTHP, right? And VSG at the very beginning is what? VDD minus 0, right?
Yep.
Which is larger than VTHP, which is good. Until this one becomes what? It's going to stop discharging.
Until it becomes less than or equal to VTH.
Mm-hmm. See, VDD, it can be VDD, can be something else. It's just VD, right? Voltage here. At the very beginning, the table is 0, for example. The table is 0, right? And here's the source voltage. Table 0, here's the threshold voltage. And discharging until your VS equals, here's the threshold voltage, until VS equals VTHP. It's going to shut off the channel. So eventually, what is being, I am discharging the cap, but you can consider that I'm trying to pass 0 to the cap. But can I pass 0 to the cap? The answer is no. So what can I eventually pass to the cap? No. Yes. Why? Because VS is VTHP. And VSG is VHG minus 0 because it's got 0. Yeah. We're in the Mason. You guys need Mason?
No, we need Mason. Where's Mason?
Too fast.
He opens it way too fast.
Good on this? All right. These are called pass gates. You will see these pass gates in a lot of places, even though they are not perfect, because NMOS cannot pass the entire VDD, and PMOS cannot pass the entire ground, but they are still being used in a lot of places because they are simple. So if you want to really design something to pass the logic, just pass it through, not adding any logic to it, right? What are the two options? So I have 1, I want to pass 1, I still got a 1, 0, and still got a 0. What are the two options?
1, 0.
No, for 1 got a 1 and 0 got a 0. How could you do that? What's the first option you have learned? The first option is inverted twice.
Why would you invert it that? Why don't you just have a wire?
Because it's a buffer.
For what reason?
Yeah.
For driving bigger cap. That's what you did in the lab, remember, yesterday?
I didn't get that part.
If you have a huge, so for example, you have a very small inverter, right? Very small inverter, which means the width to length ratio is tiny, right?
Mhm.
So you have a small inverter, then you have a huge cap, like 1 microfarad or something, or larger, okay? And you won't be able to charge and discharge this really efficiently if you have a pretty fast pulse. You know what I mean? It's going to do that, do this. Because this guy does not have the driving capability to drive that huge cap at that speed. So how do we improve it? The same pulse, same frequency for the pulse, same load. Yeah, just these are called buffers. How that works, because these guys have bigger width to length ratio. So if you look at the layout, remember, so yeah, so for example here, right? What's the one in the middle? What's this in the middle? Oh, no.
Oh, yeah, no, that's you.
What's this one in the middle? It's a gate,
poly.
right? That's a polysilicon, a gate, pink. Like that. Here's a gate. Okay, and or if you draw it the cross-sectional view, right? There's a gate. And source drain, right? Source drain. Okay. So which use in here, which dimension the length, which dimension the width of the transistor. So here's a metal one. Here's metal one. Right? Metal one. They are saying, hey, here is what? Length or width? Drain source. So current flows that way. Current flows that way. Current flows that way. That's a channel length. But it's not even accurate. So the accurate length here is the dimension of the poly. Here's the length.
Oh, no, I see it. Yeah.
Yeah. If you have a, so the length is determined by the dimension of the gate, keep in mind. And here's the width. Okay. And the current flows that way, right? And if you have a very big transistor, here's a gate. Are you having a big width or length here?
Width.
Yes. And now we look at the square law equation. If you have a big width, are you getting a large current or small current? Yeah, large current. Okay. So in real world design, if you want to increase the driving capability of the devices, you want to use big length or width? Yes. Why do you need a big width in order to increase the driving capability? Because yeah, more current. And why more current, more driving capability? Yeah. More current means you initially at the very beginning you have a tubing, right? You are trying to fill up a cup. Takes time, right? So you cannot charge and discharge it really quickly. But now you have a huge pipe to fill up a little cup. Easy.
So that's why you lab make more instances to increase the width, or yeah.
No, that'd be like
Which one you're talking about?
the one yesterday when we were creating that.
We didn't change the size of the gate, we just made more of them, right?
Oh yeah, more. Yeah, I'm gonna cover that later. That's stick diagrams. You see why it's increasing the width. Okay. So if I draw it like so two NMOSes, W over L, right? If I short them together like that, and gate shorted together. So in your layout, it looks like I can combine the middle, wait, can I? Wait, something's wrong here. Wait, they are in parallel, right? So if you look at this way, then you have one here and one here, right? Here's a gate, here's a gate. And you short the gate together. These are the diffusion and plus and VS, and you use the metal to short them together. Do you have a wider one or longer one? No, wider. Remember which one determines the length of the channel? The gate. So I have a bigger W here, right? So if you have two transistors being shorted to each other like that, it's equivalent to one transistor, but with 2W over L. Same performance. So a lot of times you can simplify the transistor in that way. Okay. However, you can make the same thing, but looks different. Looks in a different way. Do it in a different way. Like the ones we did last time. I think that one is a wider. Yeah, it looks like they are being stacked on the x as the x dimension, but they are actually in parallel. I'm going to show you why they're in parallel, not in series.
Good.
So it's, for example, two inverters. Okay. So I have two PMOS on the top. If I draw the PMOS diffusion like a circle, I'm just not drawing, this gate, diffusion, right? There are two transistors, two gates. But the middle one just got shorted together. I don't have to draw two. I can just combine them together to make one. You know what I mean? It's the same, just the contact, it's the metal contact, it's nothing else. Right? So I simplified everything like this. PMOS. Make sense? 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. Right? Equivalent. And now, if I combine them like this, how can I make these two PMOSes in parallel instead of in series?
Just short the poly together, right?
If you run current like this, if you short this one to some point, okay, and you don't do anything else, just directly run current. I just short these two gates, just turn it on, okay? Just turn it on, whatever. You can turn it on, no problem. And then run current in that way. For example, each transistor is W over L, okay? If I run current that way, I'm getting an equivalent transistor of what? 2W over 1L or 1W over 2L? You got it, great. Two lenses, right? But one width. Okay. So that won't work. That's in series. How can I put the two transistors in parallel? Still have the middle one combined together, but I want to rewire it and make the two PMOSs in parallel. How do I do that? So in layout, let me do the layout to make it looks like a real one. Okay, here's the layout. VS, gate, two transistors. Okay. Again, if you throw here to one, here to one, and run current that way, you're getting 1W over 2L, right? But I can reconnect this circuit to make these two PMOSs in parallel instead of in series. How do I do that? So got one metal one here, and make the connection. The middle one, and combine these two using metal one. And short this one to input, short this one to output. And now they're in parallel. Why is that? Current comes in, getting split. So now it's like in parallel. And flows in here, and comes to one width, one length, and merged at this point, and then go to the output. So now they're in parallel, not in series. Why? So in your mind, the best way to understand it at the very beginning is how you understand these two transistors in parallel is you, for example, you can tear this, right? And split them, right? And rotate them. And now they're in parallel. So tell me what's the difference compared to this one and this one? No difference. If I split it, rotate it, it's the same thing. Make sense? So all these vias are just wires. It's metal. It's long here is longer than here, which is fine. Just metal, no difference. Split goes through the channels, two channels, and merge. Here, if I get a metal here, metal in, right? Split, merge. Got it? So in here, how to make the connection? So if this is a VDD, this is ground. So it's gonna current is gonna go down here and split, and merge here. So that's how to do the connection for the PMOS. Okay, NMOS. Split, and go through the gates and merge. And that's an inverter.
That's the one that could be bigger.
Yes, and let's see. Oh no, it's not an inverter. What is that? It's so what is this? It is an inverter, but right? If I connect these two, gates. This is this. And this is called stick diagram. Stick diagram. Very, very helpful. If you don't know how to draw it, you won't be able to optimize or lay out in the future. So this is something you have to learn. I think we're going to spend about somewhere around a week, 1 week, to practice on how to draw these stick diagrams for a more complicated circuit design. Where we were at the inverters, right? Mm-hmm. Why the inverters have PMOS on the top, NMOS at the bottom? We still haven't answered that question yet. Right? So very quick, let's draw the stick diagram for the inverter really quick. You got one PMOS on the top. Oh, PMOS is a circle, right? Circle. Mm-hmm. NMOS crosses like that. So what's the stick diagram for the inverter?
Those two, top one goes down, down.
Yeah, it's better to do it the other way around, right? Optimize it. Just do this. No difference, right?
Yeah.
And connect the gates, input, output. Okay? And here's the inverter. Now you understand why we have a PMOS on top and MOS at the bottom. Why?
Because the PMOS is passing the VDD directly down to
because PMOS is in charge of pulling this point up to VDD because it's good at passing VDDs. And NMOS is in charge of discharge this to ground because it's good at discharge it, passing zeros. Okay. If you give a 0 here, what's happening? Give it 0 volts. Yeah, PMOS is on. It's going to pull this up to VDD. Right? What's the difference? It's just potential changes. It's okay. They're sharing whatever, right? Voltages, charges.
Yeah.
Eventually, they both becomes VDD. If you have a 1 here, what's going to happen? PMOS is off, right? NMOS is on. So discharge it to the ground. Start getting zeros, right? And if you draw the input, we're doing a DC sweep, keep in mind. Do a dot DC. I'm writing up the spice code for you guys, right? V in, for example. Dot DC, what? V in is the voltage on the sweep, DC sweep, V in. From 0 to 5. Okay, so here's V in from 0 to 5 volts. So if I put this one in LT spice and I run a DC sweep for V in, what are we expecting to see in the simulation result? Here's V out. Here, V out.
High down to 0. No, I don't think that would be linear.
So, for example, you are doing DC sweep for V in, but can you plot V in here as well?
Yeah.
Yeah. So, x-axis is V in, but I can still plot V in, right? It can be V out, can be V in. I'm just plotting the whatever you want to plot. It's probe, double click, right? Mm-hmm. So if V in is 0 volts, what is V in?
0 volts.
So I'm going to plot the first number here, the same point. So when V in is 1, what is V in?
1.
When V in is 2, what is V in?
2.
So it's linear, right?
Yeah.
That's V in. Okay? That's V in. What about V out? If I probe V out,
Yeah, and 0.
when V in is 0, V out is what? 5. It's going to be 5 for a while, right? Whenever this one reaches a point, it's called switching point. We're going to show you how to calculate it later. It's going to start to fall like that until 0, right? Make sense?
Yeah.
Okay, we'll cover more about this on Friday.